Hi guys, this time it's a teardown video again with schematic details on the construction, on the electronics, based on the full reverse engineered schematics that I made 2 years ago. This time we have a regression, some kind of regression. Well, this one is the Chinese brick that can deliver 480 watts at 300 volts at 1.6 amps. It's called HJS-480-0-300. I made a video about that 2 years ago at November 22, showing you my my problems I had with that when I received it, because it had problematic capacitors on the output. One of the capacitors had in reality a hole, and I explained why and why these things happen. Just a quick reminder, guys, this is a 60 to 70 buck power supply shipped. So if you buy these things, please remind yourself what you paid and lower your expectations. These things are working if you know how to keep them working, or how to, let's say so, to check them before you start them. It's not they're cutting, of course they're cutting corners. It's 70 bucks, come on, for a 480 watt power supply, 300 volt, 1.6 amps. Normally, if you buy that in a brand name, you will pay 10 times the amount of that. They are built without bells and whistles, absolutely without bells and whistles, as you will see. They are built very conservative. The design is more or less outdated. But hey, what do you want? You want a power supply that costs, I don't know, $600 and has microcontrollers inside, special ICs? No, these are power supplies that you will take and abuse them. Yeah, and if you abuse them and they die, you repair them. They're very easy to repair, and I will show you that. There are only three components here that if they go, they're gone. You cannot repair them. Yeah? Anyway, this is, in my opinion, for the price, absolutely a good power supply, even if many of you will not agree with me. I use that for experiments, for high impulse tests, like Tesla coils, high voltage coils, everything that you would think that would destroy a power supply. Yeah, or I wouldn't put a power supply for 1,000 bucks or so with these experiments. For this, I'm using this thing. It even has 2 10-turn potentiometers, guys. Yeah, for 0 to 1.6 amps and 0 to 300 volts. This is the display here is nice, but the ampere display is not correct. The volt display is correct. But anyway, this is what I wanted to show you for the beginning, before I start going through the schematics and the functionality of this thing. When you receive, my suggestion is, when you receive these things, use at least a dim bulb current limiter in series with that, and then put it to the mains. So if anything is falling apart inside to the transport, etc., will not make magic smoke or kill your breaker or kill this thing even more. Further, before taking it, activating it, I would open it and check it optically, visually, sorry, not optically, visually, if there is anything that doesn't seem right. And if so, correct it. Anyway, I want to show you why I want you to put this thing at least through a dim bulb tester. So I connected the power supply to my isolation transformer and variac, current limited variac. Current limited is because I have 3 dim bulbs that I can add in parallel. At the moment I'm using only one. That's a 60 watt incandescent bulb and halogen bulb. And look what will happen, what that means inrush current when I turn it on. This is what goes to the capacitors. And you see, even in the idle, there is a little current, 200 milliamps, at least more, no, sorry, 83 milliamps, flowing to the power supply in idle mode. I have it, ooh, flicker, flicker, flicker. Let's turn it. Okay, it's better now. 360 volt output, just to show you, nothing else. Yeah. Let's go a little bit more down. It's not a good idea. As possible. Anyway, this is why I always use a dim bulb tester, at least. In reality, I'm using my variac and bringing it slowly up. But if you do not have a variac, at least use a dim bulb tester. It is nothing fancy. Just put a halogen lamp or an incandescent lamp of something 40 to 50 watts in series with these things and then start it. Okay, that's the few words I wanted to say before we start with the schematic. Just a short peek how it looks inside connected, because now we'll disconnect all the cables to show you more the schematic. We have the power supply for the meters here. Power supply for the meters. We have the ground, current and voltage input, and the connections for current, the current potentiometer and the voltage potentiometer, and of course this thing, the fan. So now I will disconnect everything. Okay, let's start with the schematics. Let's go a little bit nearer, the whole thing. Starting from left to right, we have the input circuit, the mains input circuit, with an NTC, thermal resistor and a fusible resistor. After that we have this part here that you can see. That's nothing else like an AMC mains filter, comprised of 2 X2 capacitors, the discharge resistor of these capacitors, and 2 X1 capacitors to ground. That's it. This is how it looks. Fuses, NTC, fuse, the filter itself, and the bridge. After that, we have the rectification part, that is this part here. And this is the first trick what they do from old times, when you had to use power supplies for both 110 volts and 220 volts. 220, it's no problem. It's just a full wave rectification, and you have something like 310 volts here at the capacitor. But if you want to use it at 110, if you made it just a full wave rectification, you would have, I don't know, something 150 volts DC. That's not enough for the whole design of the switcher. This is why, in case of 110, they put this switch here that changes the operation of this circuit from a full wave rectifier to a full wave doubler. By closing this switch, these two capacitors and the diodes form a full wave doubler. And from the 110 or something, 115, you will get something to 310 again here. This is a trick that is used forever. Yeah. Here I want to show that this is the first shortcoming. There is no PFC circuit. There is no passive PFC and of course no active PFC, because if you had an active PFC, you had an active rectification, a universal rectification. You don't have it. In the old ATX power supplies from the PCs, when they came out in the 80s, 90s, yeah, they started to put an inductor in series of the rectifier, and in combination with two capacitors, you had quite a large inductor. You had a passive PFC that brought up the power factor up to 0.7, 0.8. Much better than without at all. But okay, this is how it is. This series resistors are just to discharge the bulk capacitors, the bulk reservoir capacitors. For the whole thing to work, we need an auxiliary power supply. I've seen many have a linear transformer, 50 Hertz transformer, and are making with two outputs, the two dedicated rails we need. But it's much easier to use a dedicated switcher. That's nothing else as a small flyback chip, quite a very cheap one and a clever one that includes the high power MOSFET. It's in current mode operated. Here you see the snubber network, and this resistor is for the current limiting, for the current sensing. Anyway, it shares the primary part, the 300 volt, the high voltage needed for that, with the 300 volt generated here on the bulk reservoir capacitors. So there's no need for a further rectification or filtering. Generated, we have two rails, one for the TL494 for the completely controller circuit, and one again for the fan and for the voltage and ampere and current instruments, displays that you have. Both of those are connected to the primary ground just for EMC purposes through capacitors. So nothing very fancy here till now. I removed my focus. I hope it's better now. So this is the venerable TL494. I like it. It exists for ages, very long, but it is a controller that gives you everything you need for a no thrills, no bells and whistles power supply. It comes with two error amplifiers, a dead time circuit, control circuit, an oscillator circuit, push-pull output that can be independent or synchronous depending on this out C pin, and the voltage reference. That's it. No microcontroller stuff, no special ICs, not too complicated things. The whole idea of this thing is to be cheap and honestly extremely easy to repair, as you will see. We have voltage and current output control. Voltage control goes 0 to 300 volts, and current goes 0 to 1.6 amps. That's 480 watts. That's a lot of power, guys, yeah. The current is controlled to this ATR potentiometer, 210K potentiometers, a multi-turn. These two. We have the high voltage sensing is nothing else as an resistor divider that goes down from 0 to 4.77 volts for 310 volts output. And it goes to the one error amplifier. This one error amplifier has its reference through these two resistors set. Sorry, no. Sorry, that was a brain fart. The reference for the voltage is generated here. This is the thing that you set, the reference, and this is the feedback. Sorry for that, guys. I'm not really 100% at the moment. They also made a nice trick here, because at these power supplies, to set the output current, you have to short circuit the output. And for that, you should you must turn the output to a very low voltage. If you forget that, you will have a bang, yeah, or it will shut down. Therefore, they made this small contraption here just to help people with this setting of the current. It is just a switch that if you put it on the L side, low side, it sets the output voltage to 5.6 volt, and by shorting out the output, you can set the current without any problems, without any risks. Remove the short, and go to the regular setting, and you control the output with this potentiometer. This is done here. This is this switch here. This thing. They even saying that in Chinese. Of course, I cannot read Chinese, but I know what this thing does. Yeah, the TL494 is here, this circuit, the controller circuit, as you see here. It is, it was not on a socket. I just removed it and put it on a socket in the time where I made the reverse engineering. This is the auxiliary power supply that you see here. Here we have the auxiliary chip. Sorry for the movement. And let's continue with the schematics. So, going from the TL494, you have two outputs, a normal and an inverted one. And these two outputs go to the drivers here. This is the driver section for the MOSFETs, this thing here. And this is the first thing, what you can see, it is outdated. This is a design that was made in the, 10 years ago. Yeah. Normally you will put here a double gate driver, IGBT or MOSFET gate driver. You could omit all of this and just put a small SOIC 8 or SO8 dual IGBT driver, MOSFET driver. Anyway, this combination of transistors are called totem pole. You have two of them, and these four form a full bridge control. They are controlling this driver transformer that has two outputs, one going to the upper MOSFET and one to the lower MOSFET. The drain source connection point here goes to the primary of the power transformer. In parallel with that transformer, you have a snubber circuit. I will show it to you in a moment. And the return goes through a DC blocking capacitor back to the middle point of the bulk capacitors, loading capacitors that have the half of the top voltage, something that 160 volts or something like that. The whole thing looks like that. Here you have the power MOSFETs. You have the driver transformer, and this is the driver circuit, what you see here. Yeah, outdated, but it works. Who cares? It works. These two parts are the snubber, the resistor, and the capacitor. And this is a very critical component here called the DC blocking capacitor. I don't know if you can see it. It is 4.7 microfarads at 400 volts. This is a little bit, the voltage is a little bit low rated. I would use 600 volts for that. This capacitor here is very, very critical. It takes a lot of beating because it takes the whole high frequency AC current that goes, the switched current here, up and down, that goes through the low resistance primary coil to the 310 volts. Everything goes through this capacitor. Theoretically, this capacitor should be dimensioned like that at the switching frequency, it should be a dead short for that frequency. But this capacitor, if it is the wrong one, and honestly, I don't like this one, it works, I will leave it. I would put normally a Chemet or a Vishay, an MKP capacitor, a pulse capacitor. Instead of that, 600 volts at least. This thing goes. And if it goes, you can only hope that this will get hot and will disconnect, or the fuse will blow. Otherwise, you have dead MOSFETs. Without using this capacitor, this DC blocking capacitor, you would have a flux run away on this transformer here. With every change of the cycle here, this transformer has to reset. And if you have an offset and goes not all time to the same potential, and if you have an offset without using this capacitor, this transformer, the flux will go like that, like a staircase. And at some point, you have it in saturation, and then you have a dead short. And then this will go, these two MOSFETs will go. And if the transformer, the primary, has too thin windings, rip, rest in peace, my friend. And this is the worst thing that can happen to you at this power supply. Another thing I want to mention is that they use ferrite tubes for EMC compression on the MOSFETs, on the drain and source of the MOSFETs. I don't know if we can see it. No, I think we will. Look, these are the tubes that I mean, the ferrite tubes. And on the other side too, on both sides. So this is the blocking capacitor. This thing is one of the first things that normally goes when the power supply is all the time in full load or for a long period of time. I changed a lot of those. Yeah. Let's continue. Now that we saw the whole primary stuff, let's go back. Let's go to the secondary side. The secondary side uses two double diodes, one in a package with a common anode and one in the package with a common cathode, connected to a full bridge rectifier. Again, a snubber circuit in parallel. These are the power diodes, two diodes. I will show it to you in a jiffy. And normally, this high value inductor is put here. You will see it mostly here. But by putting it on the ground, on the return side, you eliminate or make the emissions that go, the electromagnetic emissions that this thing generates if it would be on there, because you have pulsing here, much less. So this is why they put it down there in series with the shunt. Then you have the two shunt resistors in parallel, and in parallel you have the ampermeter. So, output capacitors, discharge resistor, and minimal load resistor, so that you have a regulation. Parallel to the output and before the shunt, to not have an error of the burden voltage of these shunt resistors, you have a voltage meter. That is more or less the whole thing. It is a classical half-bridge design, no frills, no bells, no whistles. Works because this is how it is designed to work, this thing. They didn't do anything additional. It is more or less a beautiful design of an application note, of a standard from Texas Instruments and from Unitrode or whatever, yeah? This thing is, yeah, you can put whatever you want here, that has two dedicated output rails. And the whole circuit here, what you see, is fully generic. This will be the same circuit with other values and other transformers for every one of the series of these power supplies that are using a half bridge. So for all these where is it here? This HJS something series for 48 volts, for I don't know, 24 volts will be the same. If it is a half bridge and 480 watts, then it will look like that. You will just have different transformers. This transformer, probably this will be all the same, because we will use the same MOSFETs because of the 480 watts. No other difference. This will change and the output capacitors will change. What I would suggest when you get such a power supply is to, first of all, make an optical inspection. Make an optical inspection if anything looks dodgy. For me, I had these three capacitors were repurposed. That means they were taken from a scrap power supply or a scrap PCB, and they're taken it out in that way that they made a hole in one of the capacitors. I changed these capacitors with nice Nippon Chemicon, 400 volt instead of 350 volts. So this is what if you have a power supply that is above 48 volts or something, change this and put low ESR capacitors inside. This is the first thing that will keep your mind clear, nothing else. Here is the output choke, the 3.3 millihenry choke. They use a thermostat here that if this goes hot, it turns on the fan. The fan pin is that. And these are the two output Schottky dual diodes that I showed you on the schematic. That's it. That's the whole schematic and the whole design. Guys, if you like what you see, if you like my videos, if you like my content, and if you like my beautiful voice today, please subscribe to my channel, like my videos. This will help me to show you much more of these things, make more reverse engineer, more designs, more teardowns, more everything. Yeah? I have a lot of content to show you for almost every aspect of electronics except of audio. I'm not into audio. Interesting, never was. Anyway, this is how it looks. It's not bad at all. At the end, if you do not have it destroyed one of the transformers, either this one, or this one, this thing is indestructible. It is completely repairable, everything. If this one is dead, sorry, game over. This one, perhaps you can find something. This one too, perhaps the trigger transformer. But this one is game over. Then you have to find one that matches what it was in there. Everything else is fully repairable. So this is what you get for 60 or 70 bucks shipped. Do not compare it with a high precision, brand name, UL certified, CE certified, whatever certified power supply. No. These are crude power supplies, but they work. And if you be cautious and check them optically and see if there are any damaged things when they came, they will serve you quite good for abusing them a lot. I use this, as I said, for in abuse situations where I don't care if this thing dies or not. Yeah? I just want to make my tests, and even with a short circuit, who cares? I will repair it. So take this power supply with these thoughts. They are very, very simple, but they do what they should do, just to give you more or less the specifications that are written on it, more or less. Yeah, take it with a grain of salt. This is the schematic again, completely reverse engineered, not bad at all, and absolutely standard, a legacy. Nothing special. So that was it from today. Look what I'm speaking for today. Guys, I'm sorry again, I'm not 100% on. Thank you for watching. Please subscribe. See you next time. Cheers, guys. Bye.